You want to move the table there that you can face the computer in front of you?
I'm going to walk about, that's right. Okay. I'm going to walk about. Right, I'm LYNDON. Vigier was called a heretic. These days I'm called a crank. Last time I looked, I'm crank number 2 on the internet in cosmology. Thank you. And from there, my background is, I'm a teacher, I'm proud of it. Yes, I've got a physics degree. I went to the best university in the Northwest, Preston Polytechnic, and did a research degree there on solar cells, working with ICI. And the idea there was to get the photons absorbed in the depletion layer. What I then did when I got interested in cosmology was to look at it the other way, not the ones that absorb, the ones that are transmitted, and apply the same principles here. Now, just to get in the right mindset, for the next 45 minutes, there was no Big Bang. Never happened, fairy tale. For the next 45 minutes, the universe is not expanding. Never did, never will do. Okay? We've got a static universe. Now, there is no evidence of galaxies going whizzing away at high velocities. That is an interpretation on results. What is measured is that characteristic lines in the spectrum of distant galaxies have a longer wavelength on arrival than when they set off. That's what we have to explain. That is the experimental result. It's also distance dependent. That is, the further away the galaxy, the further these lines, the bigger the wavelength of these lines when they arrive. There is around us microwave radiation, which may or may not be linked to the shift in wavelength. Now, what we're going to do here is look at tide light. Lots of tide light theories have been around. I want you to forget those entirely. This is completely different, and that's why it's called new tide light. Some of you have seen papers that are said disprove tide light. I'd like you to put those to one side, forget that, have an open mind. The plan is 15 minutes we're going to go through tide light. We're going to derive redshifts and the CMBR from first principles. Okay? And do that. Second 15 minutes we're going to look at the evidence for and against tide light. The last 15 minutes we'll take some questions. So if I can get this to work, I will go on from here. Not new. I first published my first paper. I published on this in 2006, and there's about 9 or 10 more since then, including in 2016 Vigier. The game changer came with fast radio bursts. Up till 2 years ago, it was always if the number density of electrons in intergalactic space is this, then that would happen. With FRBs, we can actually determine the mean electron number density. And this is, there was one earlier by Keane in Australia, and foolishly I relieved him and worked it out and published, and of course it's now decided that he got it wrong. Now we're fairly confident on this one because it's a repeating FRB. Fast radio bursts, we get these unbelievably intense bursts of radio for a very short time period. And it's got what's called a dispersion measure. Go remembering school physics, light going through a prism, red bends the least, blue the most, and that's dispersion. And it's to do with the velocities. And this happens with radio. The frequencies come in, boom, 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 in order. And by measuring the time delay, you can get the dispersion measure. So this is our FRB there. The DN, that's for the Milky Way, that's for the Hale around. We don't know the most, so especially 340 of them. The angular distance 683, luminosity distance 972, and we've got redshift. We've got a complete set of data here. And so what I'm going to do is to take the dispersion measure here, and the distance, I'm taking dA because this has got Big Bang fixed into it. So I'm going to take the distance and the dispersion measure. I'm going to determine the mean electron number density along the path. And then I'm going to use new tide light to predict the redshift there. So that represents success. There's the answer in the back to book. Let's put it here. That's what we put in, the redshift. So that's the plan. Quickly, let's just going over tide light. And basically, intergalactic medium, cold plasma. That is, you can forget thermal motion, and all the motion of the electrons are affected by the electrostatic forces only. Now, it's well known, electrons in cold plasma perform SHM. The electron moves forward, then the space in front becomes more negative, the hole behind the positive is pulled back. They oscillate. And any electron that can perform SHM can absorb and emit photons. This is going to go? Oh, I missed it. Sorry about this. Oh. So, this is a pathway. When you look at a distant galaxy, a photon sets off. It battles its way across the space for millions of years, avoiding dust and everything else. It arrives, comes into your telescope, and enters your eye. Nobody else gets that photon. That is your own personal photon with that galaxy. And what I'm going to do today is trace the path of that photon as it goes along. As it goes along, it'll be absorbed by an electron, which will oscillate and emit a new one. And the point is that there's a delay between it being absorbed and re-emitted. Okay? And during that delay, it's absorbed, that electron's going to recoil. And so some of the energy of the oscillating of the photon is transferred to kinetic energy of the electron. It's lost to the photon. So when it emits a new one, it will recoil again, more energy lost, the energy of that photon is less, the frequency is less, the waves are bigger, it's being redshifted. Okay? Now that energy transmitted by a recoiling electron is given out, and that forms a CMBR. That's the plan. So, carrying on, boom. Here. That's what we've done. We've got our redshift, we're okay on that, boom. But this, so Hubble's law then, in tide light, photons of light from a galaxy twice as far away, make twice as many collisions with electrons, lose twice as much energy, undergo twice the loss in frequency, and so if you get something twice the wavelength. That's the Hubble law that we're talking about. Now let's move on. What we're going to do now is, because we're going to do this from first principles, the measured frequencies aren't precise enough. So I'm going to take a photon in the UV. You'll realise why it works for any photon you like. And I'm going to choose that one. I'm going to cherry pick just this talk because I'm limited. And I've got 9, 10 stick figs there. That's why I've chosen my own. Experimental ones don't have real stick figs. We're using the calculator free online from Casio, which can do up to 120 digits. I'm using 14 because it's all going to happen around there. So we need to have it precise. So there's my photon in the UV, comes along, I can get my momentum, beeps out to a lambda, and that momentum, by conservation of the momentum, will be transferred to the recoiling electron. When I do that, I get my speed of my electron at 14,500 meters per second. So we can use classical physics from there. So there's my recoil. Now that takes the form of kinetic energy. So I can work out the energy transferred to my recoiling electron. There's a recoil, just half mv squared, which is that. That's then radiated as a secondary photon, CMBR. Now if I look, there's my energy equals HF. I can calculate the wavelength, you get 0.21 centimeters. Now how does that compare with the CMBR pump? Is it going to go? No. Come on. Hang a minute. Where's it gone? I've lost my slide. Oh well, never mind. That's actually the peak of the CMBR. It's bang on. The CMBR peaks at 0.21 centimeters. Oh there. I might have lost that. There should have been a picture of the CMBR there. So that one photon, so I picked it, gives me secondary radiation at the peak of the CMBR. Other wavelengths are formed by other radiation. Visible light has a lower energy, so that gives out lower energy CMBR. Now, it is known and well and documented, plasma emits black body radiation. So we've got our CMBR, we've got this black body, that's, tick the box there, we've done it. So let's go back to our initial photon. It came in, absorbed, electron oscillates, recoils, that CMB photon goes off. It then emits a new photon that way, electron recoils again, CMBR photon's given out again. So it moves on. So what we now want to do is, we've already seen the energy of our recoiling electron, double it because of two recoils, one there, one before, and then I can work out my energy of recoil is that, half mv squared, and I'm going to subtract that from the initial energy of my photon, just to find a new wavelength. It's interesting here that in new tide light, recoil takes place along the line of sight. So it doesn't deviate, it goes in a straight line. There's no blur, no scatter with new tide light, because the recoil is that way. And then at the end, please. So there's my energy there. So I'm going to now, there's my initial energy, subtract it from there, gives me that. There's here, we've got new wavelength, and there's my new wavelength, you see it's happening around there. And I get my increase in wavelength on each interaction, 2.426 times 10 to the minus 12 meters. You get the same answer regardless of the wavelength you use. Now some of you might recognize that as a famous number, but we're going to carry on. The same result at shift in wavelength, whatever the initial wavelength is. So, let's then find out. We've got our FRB, we've got a dispersion measure. This is a standard formula, and we can work out there that on average on that line of sight, N number density on average 0.498 electrons per cubic meter. Okay? So we now know how many electrons there are from our FRB. Going on. Now, down to probability the next. We need to work out the collision cross-section. That's the chance, the probability of it bumping into an electron and being absorbed. Now these are known by a guy called Hubble actually, and from Berkeley Labs, Lawrence Wright Laboratories, Berkeley, and they looked at the interaction of low energy X-rays and atoms. And this is the published collision cross-section. Now this is for it being absorbed. F2 is the probability, basically that's the probability of being absorbed, that's the probability of being re-emitted. F2 for hydrogen varies between 0 and 1, it's 1 electron. F2 for helium varies between 0 and 2. Lithium, F2 varies between 0 and 3, there's 3 electrons there. So what we want is, and it all depends on the frequency of the incoming radiation and the resonant frequency of the atom. If you're well away from the resonant frequency of the atom, F2 is 0. Doesn't get torque is transmitted. If it's bang on the resonant frequency, F2 is equal to the number of electrons, and so it's absorbed. So what I want here, that's the probability of being absorbed, that is the probability of it being emitted, and F2 is 0, so I get my collision cross-section for my photon. When I put the numbers in there, I get the sigma probability collision cross-section 2.818 times 10 to the minus 21. That is for my photon. Now, going on here. Oh. We then need the mean free path. That's average distance between interactions. Mean free path, n sigma minus 1, stick it in there. The mean free path of my UV photon is 7.1 times 10 to the 21 meters. Put it another way, the photon coming from a distant galaxy, by FRB, interacts with an electron once every 750,000 years. If it's visible light, it would interact once every 75,000 years on its journey. And each time it interacts, we get the shift in wavelength that we've got there. So there's my mean free path. We can now work out how many interactions it makes, which is the distance, total distance, which we have from our FRB, divided by the mean free path, and I get 2,954 interactions on its way. Each time it makes one of those, I get a shift in wavelength of this, so my total increase in wavelength is 7.1 times 10 to minus 8 meters. Now, going on here, redshift, defined as delta lambda over lambda, I get 0.1433, which is quite close to 0.19 as the measured value. We're out by 20%. Everything you've seen there is referenced, it's standard physics, there's no need for new physics, and it's not bad, I don't think. We need more data so we can get more done. We need more FRBs. Now, redshift here is a constant for all wavelengths. Now, why is that? And the answer is through the collision cross-section. That is, a photon with a wavelength twice as big, has twice the collision cross-sections, makes twice as many interactions, undergoes twice the increase in wavelength. So you divide it by the original wavelength, it comes out as a constant. So we're okay there. So that is there. Now, I said this has been published many times. If you do it by algebra, that's the form you get for redshift and H. That's my H, 2NHR over M. N is the number density, H Planck constant, R classical electron radius, M the mass. And we get a value of Hubble constant, 2.04 times 10 to the minus 18, which is 62 kilometers per hour per megaparsec. I think the most recent value is 71. So we're not bad on the Hubble constant either. Now, where are we to? So we're about on time now. Let's then have a look at the evidence against it. We're getting the right answers in the back of the book. Everything's going well. Is it a coincidence? Well, let's look at the evidence. One, total surface brightness test, often quoted as being proving tide light wrong. The idea we look at the surface brightness for a galaxy is supposed to vary as 1 plus z to the minus n in tide light. N is supposed to be 1. In expanding universe it's 4. What they got was 2.59, which to me looks like splitting the difference. It doesn't, but it was said here that this disproved tide light, but agreed with expansion. Splitting the difference. Now, Lerner, what he did was look at looking bigger redshifts, so the effect was greater. And looked at the redshifts from 0 to 5, and he found that the data supports a static universe, not an expanding one. Okay? So we can forget. Surface brightness is with tide light. This is something I did for a conference a while ago. What we're looking at here is the Lyman alpha forest. When you look at distant galaxies, which are supposed to be, I think, right the other side of the universe, as they come along, as they go through hydrogen clouds, then the Lyman alpha absorbs a particular wavelength. It then carries on, next one absorbs the same wavelength again, but the light's been redshifted as it goes by whatever means. It goes through the first hydrogen line, boom, puts a black line on it, absorption line. It then goes along, but it's now redshifted, so that line moves, it's the next hydrogen cloud, boom, puts another one on. What we've got is a ticker timer. You go back to school, these things that put dots on the tape. And what these do, if you remember the ticker timers, the dots are evenly spaced, then, well, it's the distance. In the expanding universe, you expect that the clouds get further apart. So you should have fewer and fewer lines. And that's what you've got here. You've got basically expansion. Everybody was happy until this happened here. That is, for the last billion years, these hydrogen clouds are evenly spaced. Now, of course, the question is, and we're going to come to supernova in a minute, that region includes most of the supernova set to show expansion. So what you've got is supernovas say, oh, everything's whizzing apart, and yet by some miracle, they happen to be hydrogen clouds in that space, they're evenly spaced. If we take this evidence, let's move on. As you know, I'm British, most of you are European, so that's European Space Agency. And you'll find this hidden away on their site. Again, this is the one I'd done previously. And here you can see, if we take this evidence as it is, what you've got is the universe expanding here. Hydrogen clouds going further and further apart. So the fewer and fewer of them within the same distance, and then it stopped expanding here and it's been static. We've got the scenario of the density, being the critical density, that is, the universe expands, critical density enough, and it just stays there. And that's what the evidence is telling them. European Space Agency. But you will need redshifts, and those redshifts will be formed by new tidal light from there. What else have we got? The universe started a big, hot Big Bang, so we're told. And since then it's been cooling down. Well, we can get a measure of the temperature of the universe, what's called a Doppler parameter. And this comes from the width of those black lines. And if it's a measure of the half width of the line. Then the more disorder there is in the cloud, or the hotter it is, the Doppler parameter is bigger. Now this is in the past, this is in the future. And what you've got there is a universe that's constant temperature. At best, getting hotter if you take it on face value. It's certainly not showing any cooling down. So, where's the evidence for this cooling down? From there. What else have we got? Now this is LYNDON. This is the data which, if you're on the internet, everyone will produce this and say, this is proof that tidal light doesn't work. This is looking at the aging rate of supernova, that's the width of the light curve. When they go with a bang, it goes up and then down. And they're looking at the aging rate. And that, with no time dilation, that's a static universe, it should be a dotted line. With Big Bang theory, it should be like that. Okay? And it looks beautiful, doesn't it? It looks too good to be true. And the reason is, it's too good to be true. Because they're not supernova 1A. They've been declassified. Of the 20 here, what they've done is 20 here, they've used these 20 supernovae to produce a template. 20 there, and then they've applied it to different supernova at different distances. And I'm sure at the time they did it, they believed they were supernova 1A. But the Union 2.1 compilation, and I quote, this all supernova currently classed as S1As. But when I checked this, there were a lot of them missing. So I wrote to them, said, where's all these supernova gone? Basically, of the 20 there, 16 have been delisted on the basis that they're not in the Hubble flow. The redshift isn't accurate, but that's fair enough, it doesn't affect things. Of the 13 high supernova here, there's only one currently thought of to be supernova 1A. So what you've got is not this, I think it's that one and those. Now, if you interpret it that there, yes, it's still showing that there might be some time dilation, but it's nowhere near as convincing as it was then. So let's keep on those. This again, something I did for a paper a couple of years ago, and looking at supernova like the hydrogen cloud. Are the supernova getting further away? In fact, in the past, when the universe was small, I should have more supernova closer together. Present now, there should be fewer and fewer because the universe is expanding and going. And there's two interesting things. One along here, basically the same, evenly spaced. So you've got the things, the universe is expanding, so the distance between supernovae getting smaller and smaller, they must be popping off at a greater rate to keep the number the same. But what about this one here? The local ones. This is all the supernova 1A data. There's something strange going on. And this is where they take the template for nearby supernova to compare with time dilation. Worse still, recently published, we've got this. There's two types of supernova 1A. And they're different. And it's distance dependent. Here, 70% are UV red, 30% blue. Over there, you get down to 90% blue and red. They're not the same supernova, and yet they're using the template on these supernova to get the distance over there. Okay? Could it be a curve broadening? It's not time dilation. This is an interpretation again. what happens is that the width of the curve seems to get broader and broader as you go along. Now it's known that the brighter the supernova is, the broader the light curve. It could well be that it's a Malmquist bias. That is that as you look further away, you don't see the dimmer supernova, you only see brighter ones, and they're going to have a broader light curve. I'm not answering that, I'm just saying, some people say it could well be. Let's then have a look here. This is Crawford, 2017, who's looked at the supernova data and raw data, and come to the conclusion this SALT 2 is how to make the template from the local supernova. And Crawford's of the opinion that it is a figment of the sun. If you use the raw data and don't process it, you end up with no time dilation and it's consistent with the static universe. This is M. Hawkins, met Michael, 2009. He's with the Royal Observatory in Edinburgh, and he's got 4 or 5 papers along with others because quasars have light curves. And Michael looked at 500 quasars to look for time. He's got 4 or 5 papers on this. 4 or 5 papers, 500 quasars, no evidence of time dilation. Well, if quasar light curves don't have any time dilation, supernova shouldn't have any time dilation unless it is intrinsic to those supernovae. As far as I'm concerned, until we sort this out, forget supernova time dilation. From there, it's got to be both or none. Okay, that's the end of the talk. Bit of an advert for you there, and not quite sure what time it is, but if you have answer questions, 10 minutes. I would do questions. Any questions? Yeah.
Could you go back and try to say what a photon in this terminology is an electron? I think you mentioned somewhere that the line continues, the photon continues in a straight line.
Yeah.
Why is that?
It's the way in which the recoil takes place. The photon's going this way, hits the electron, and recoil elects that way. There are other, some people say, one of the objections people have put forward Compton scatter. The problem with Compton scatter is that there's no mechanism where it can store the energy. So with Compton scatter, the photon's got to be absorbed and re-emitted at exactly the same time. So the only way it can recoil is if the photon goes off at an angle, which gives you blurring. Now with neutron light, we're saying the photon comes along, absorbed by an electron, which then recoils in that way. Because there's a delay, when it goes off again, it recoils back. It doesn't deviate, it's straight. Yeah?
Because I know the redshift doesn't depend on the frequency. In your
That's
theory,
right.
I'm using it's not so clear. Why it doesn't depend at all? Doesn't depend at all.
Exactly, and it doesn't in neutron light because of the collision cross-section. Right?
But condition maybe depend on the energy.
No, it's the redshift is the ratio of the shifting wavelength divided by the wavelength. Yeah. Now, if you've got, say, a wavelength of light, frequency, whatever you get to the wavelength is twice as big. Collision cross-section is twice as big, makes twice as many collisions, loses twice as much energy, has twice the increase in wavelength. So when you divide twice the increase by twice the wavelength, redshift comes back to being Z. Yeah. Yeah, no, that's a good question. Anything else? Right, well, let me just last 5 minutes if I've got 5 minutes. The commonly, where are we going? Often it's asked for lab tests. This is one of the problems we have, is how do you test it in a laboratory? The thing about tidal light is it only happens in the sparsely populated intergalactic medium. And when the plasma gets denser, then the forces on it are higher, the electron doesn't recoil. One of the problems with previous tidal light models is you're going to get twice the shift in wavelength as they get to thick plasma around the Earth. It doesn't happen because it doesn't recoil then. Okay, all right? Yes, here I go.
You agree that there is no evidence of time dilation?
The trouble is, this Big Bang is everywhere. They don't measure time dilation. The experimental result is the light curve of supernova will get wider the further they are away. And it could just be that they're brighter supernova. This is an interpretation, just as nobody measures velocity of galaxies, they measure the shift in the wavelength. They've got a longer wavelength here. Yeah?
The same phenomenon of tidal light can be observed also in a potential ether. If we admit the hypothesis of presence of ether, the same phenomenon must be explained, no?
For me, the ether would be the plasma of interacting space. That's what light travels through. Yeah? I'm not sure if I heard right. I'm a bit deaf. I've got spent.
I am a supporter of the ether.
Right. Well, for me, that would be the plasma. That's what light travels through. It travels at the speed of light between interactions, but because of
But I
delays.
suppose that the phenomenon will be the same as you described in the hypothetical ether.
And treating space as a transparent medium.
Thank you.
Yeah.
So that cold plasma, what does it consist of? Just electrons? So it's all negative, or are there positive charges?
The positive charges are as well, because overall it's neutral. But the point is, because
that's protons or whatever.
Yes, a proton and electrons,
Okay.
but electrons don't attach the protons.
No.
But you can ignore the motion of the proton because it's so much more heavier. In effect, it's only the electrons that absorb and re-emit.
Okay. How much is it generally accepted that this kind of cold plasma exists at all?
Sorry, again?
To what extent is it accepted in the astronomical community that these cold plasmas exist and are stable?
The cold plasma is well established.
Okay.
That's well established.
Okay.
And you'll find that all around. You will. But as for me, I'm here. That tells you the answer to that question.
5 minutes.
Okay. That's it. Okay, thank you.
Well.